Saxon Advanced Mathematics, lesson 59. We have a two-part lesson. Both parts relate to logarithms. As you can see, we're going to do some fancy stuff, but I want to kind of create a picture of the world of logarithms that we've studied so far and help you see where we're working. Our study of logarithms has been divided into two parts. Sometimes we do actual calculations. We use the calculator, we use those 4 buttons, and we convert the log expressions into actual numbers. The other side is where we're basically just working on rearranging and simplifying. This in particular is where we have used the laws of logarithms to help us accomplish that. And I'll give you a quick recap. If we're adding 2 logs with matching bases, we can multiply their arguments to combine them. You're copying, I know. I'm writing really fast. If we are subtracting logs with the matching bases, we can divide their arguments. These look very much like the rules for exponents, don't they? This is like the product rule. This is like the quotient rule. There is a third law for logarithm. It matches to the third rule for exponents, which is the power rule. It looks a little bit different though. The third one is useful in situations where we have a coefficient in front of our log expression. We can take that coefficient and pop it up as an exponent. And conversely, if we have an exponent that we don't like, we can pop it down as a coefficient. These are the tools that we use when we're working on these rearranging and simplifying style problems. We could use these over here, but we tend to use them less. All right? Now, today, we're going to take this category and we're going to break it apart into 2 different types of rearranging / simplifying problems. The first one looks like this. Something like this. I'll give you a second to copy it. I know I'm going too fast, I'm sorry. The situation here, if you'll notice, is that we have a log expression, a single log expression on the left, a single log expression on the right. In this situation, we can pop off the arguments. And what I mean by that is that we can say x plus 2 equals 5. There is a theoretical explanation I could give you as to why we're allowed to do that, but right now my sense is that your brain probably doesn't care. It's just important that you know we can pop off the arguments, which is that part, and we can just deal with that and then solve it, of course. We'd subtract 2 from both sides and we'd get x equals 3 as our answer. And then we always have to test to make sure that the argument is positive. 3 plus 2 would be 5, right? So we have to test. I'm going to put it here. Okay, so it's true of anything, but especially in this style of problem, we have to just check and make sure that that makes our argument positive. Okay, so this is the first kind, log equals log. The other kind of rearranging and simplifying problem looks slightly different. The numbers aren't the part that matters. What we have here is we have a log on this side, but then equals 2. There's a plain number on the other side. Okay, this is different. This is what we want to, our strategy here is change to an exponential equation. I'm not going to write that out. You know what I mean. An exponential equation. That's our strategy here. So what we remember is that this is the base, this is the exponent, and this is the number, right? This is what we get. So we can rewrite this as the base raised to the exponent equals the number, right? And then we can calculate from here as well. 16 equals x plus 5. We subtract 5 from both sides, and we get 11 equals x. Again, for this style as well, we have to make sure that we test the argument to be sure it's positive after we could do the calculation. So we take the 11 and go 11 plus 5, 16. That's a positive number, yay. Okay, so this whole picture helps us see the different types of problems. And like I said, today we're going to be working on clarifying the difference between these two. Yes, that's all I want to say. There's a cat standing on my page, blocking my camera. Oh, it's moving. He's moving on. That's serious. That's my tuxedo cat. Okay. Look, it's new notebook day. And I'm using this little, it's a smaller notebook. This is lesson 59, continued. Okay, so let's do the first example. Those problems that I showed you were just like illustrations. I don't know, is that a thing? Can we call them illustrations? Solve. Ready? This is too crowded. I'll write it down here. Oh, the very first problem, and I'm already unhappy with how it looks. Okay. How do we know what to do with this problem? Now, a lot of times, if we see log 10, that means it's a calculation problem. If it's a weird, because our calculators do have log 10 and they have log E, the natural log, right? The 2.71, whatever. Those are the ones in our calculator. So usually if we see one of those logs, that's a pretty good hint that it's a calculation style problem. But in this problem that I'm looking at, we can see examples of where we're going to be able to use law of logs, right? Here's a subtraction, here's a power rule one. So that gives me a pretty good inclination that I can use the laws of logs to simplify this. This is a rearranging / simplifying style problem rather than a straight calculation. So what should I do first? I think I'd like to fix this first. I want to use the equivalent of the power rule, and I'm going to pop that up. So I'm going to say log 10x to the third equals, and because this is going so well, I'm going to go ahead and take care of this on the other side. So that's the quotient. I'll use both of these rules to fix this. And then this one I know what I do is I take that and then I divide. Make sense? So I used two rules at once. They were separate enough that I felt comfortable doing that. So now I have a much cuter expression. This I know simplifies to 8. I can do that. And now I see, oh look, log 10, log 10. This is the first type. This is the pop-off style, right? And I can take the arguments off, so it will become x to the third equals 8. And that can be easily solved by taking the cube root of both sides. X equals 2. My final step is to check and make sure that this still yields a positive argument. There it would be 2. That's the only place where we have the variable in the exponent. Obviously, if our arguments are numbers, we don't have to worry about it because this doesn't have anything to do with that. It's where we have variables in our argument that we must check to make sure we have a positive number. 2, we're good. Okay, fabulous, right? So far, so good. Let's try another one. I'm going to switch pages. The ink bleeds through on these, so I'm just going to write on one side. 59.2. Ready? Here we go. This is log 7. So immediately that makes me think, oh, this isn't a calculation style. This is a rearranging style. And as I write, I see things that I definitely can use the law of logs. As soon as I see that plus sign and the matching bases, I go, oh, okay, I know what to do about that. And then it's equal to 1. Aha! This 1 tips me off. I'm not going to be able to get log and log, and I wouldn't want to subtract that or do anything like that. I want to simplify these two using the product rule equivalent. This one, right? If you're adding the bases, you can multiply the arguments. I'll do that with these, and then seeing that over there makes me understand, oh, this is an exponential style. So let's fix these first. Let's use the product rule. And we'll say log 7, and then we multiply these, right? X plus 1 times x minus 5 quantity on both of those. Oops, I forgot the 1. Okay. That equals 1. Okay, now I'm ready to switch to an exponential. This has been combined, and now I'm ready to say this is the base, this is the exponent, this is the number. If you ever get confused about that, put this into your head. If we have this log expression, we know that it means 10 to the third power equals 1,000. If you memorize this, it will help you make these conversions to exponential equations a lot easier, because I go, oh, okay, that's the base, that's the exponent, this is the number that goes on the other side. You can follow this pattern as you do the same here, right? I can go, okay, that's the base, and this number is the exponent, and this whole beast is what goes over there. That's kind of a lot, isn't it? But a few little binomials are not going to freak us out, right? So let's go ahead and multiply this out. I flipped that side over. I don't know what I did. I want to put this back on the left side. So I'm going to say, oh, just a second. I'm copying. This is a minus sign. That's a minus sign. There. I copied it wrong just there. Okay, so my binomial, you can multiply it out if you need to, but at this point, a lot of students can do them in their heads. So I know that it's going to be x squared, and I know I'm going to add these two to get the middle term, so that would be minus 4x, and then I know I'm going to multiply those to get the last term. We can go back and forth between binomials and trinomials, quadratics, pretty easily at this point, so feel free to do them in your head if you feel comfortable. If you don't feel comfortable, you can always multiply them out, do the dance thing. That's absolutely fine. Okay, so this is all equal to 7. All right, Let's pull the 7 over to the left and pray that we can factor this by inspection. I don't want to haul out the man-eating dragon if I don't have to. All right, so I just bring it over. X squared minus 4x minus 12 equals 0. That cancels. All right, two numbers that multiply to 12 and minus 12 and add to minus 4. Ooh, I can think of them. Can you? I'll give you a second to think. John is kind. He's a benevolent mathematician. Let's just call him that. That's what he is. Did you get it? I bet you did. So that means, using our zero product theorem or zero factor theorem, whichever you like to call it, x equals positive 6 or minus 2. That is the answer we calculated. However, whenever we have variables in our arguments, the argument is this part, the part that comes after the log word, we have to check and make sure that they're a positive number. 6 plus 1 is 7. 6 minus 5 is 1. 6 passes the test. Minus 2 plus 1 is minus 1. Oops. And then minus 2 minus 5 is minus 7. Ooh, minus 2 does not work. It fails. So our final answer is just x equals 6. And if you were doing this as a review problem or a test item, I would want you to show it just like this. Show me that you calculated both. Show me that minus 2 fails the test. I don't want you to copy it over and just write x equals 6. I want to see that. That looks good to me. All right, beautiful. So there's an example of how we would work an exponential style problem. And again, the clue, the big fat clue that told us that this was exponential style is we had logs equal to a plain number, right? Just like here, logs equal to a plain number, log equal to log. All right, number 3. Again, that random base says there's nothing we can do on the calculator to help with this. So this is definitely going to be a simplifying, rearranging style. And we've got some logs over there. We see power, and we see some laws of logarithm possibilities. And then the right side is equals 2. Aha! So we'll clean up, and then we'll convert it to an exponential equation. As soon as I see the plain number on the other side, I feel content with that. All right, let's take this 2 and let's pop it up. And then we're subtracting this other log, matching bases, so we can put that in the denominator. All right, so far so good. Now, we're going to convert this to an exponential equation. And remember, I'm going to write this out again because it's super helpful in helping us remember where all the pieces go. This is the base, right? This is the exponent, so we can write 3 squared equals, and then this whole thing is the number. Okay, now we can lay aside our logarithm skills and just do some basic algebra. This we know is a 9. So let's cross multiply to bring it up, right? 9x minus 18. I'll distribute, right? As I bring this up, I'll distribute the 9 against that. Equals x squared. Okay, we're building toward a quadratic again. Let's move these guys over here so that they're with the positive x squared, but let's rewrite it so all that is over here. So I'm bringing this over, x squared. This will change sides, so that will become minus 9x, and this will change sides, so it will become positive 18. I did a lot of that in my head. I hope you feel comfortable with that. All right, once again, we pray that John is kind. He's a benevolent man. And let's see if we can factor this by inspection. The fact that I wrote that down is your tip-off that it definitely is factorable by inspection, because I wouldn't have written that if there was a chance that I couldn't. So I'm looking at notes. So, okay, ready? What multiplies to positive 18 and adds to minus 9? Think for a second. Yay! Okay, using our zero factor theorem, I like to call it. Zero product theorem also is the name for it. We get 6 and 3. All right, these values, just the fact that these are positive doesn't necessarily mean they're okay, right? It's all about what happens when we put them in the argument. Well, here it's just a plain x, so either one is fine. And then here it's x minus 2. 6 minus 2 is 4. 3 minus 2 is positive 1. It's still positive. So both of these guys pass the test. Yay. Okay, that is our, it's not really a review, but that's our recap of where we are in the world of logarithms. This is the calculations for things like, no, I don't want to say anything more about that. We had certain kinds of word problems that we used and we calculated answers using log buttons on our calculators. That's the kind of problem that are here. We've been working a lot more on this style. Okay, I want to teach you about one more kind of log problem that, you guys, it's so easy, it's confusing. So let me show you. John has a weird name for it too. I'm not going to share John's name with you until after we explain it and get it. But this is a different kind of advanced log problem, and it works like this. And let me just tell you, there are a total of 9 problems, but they're all on this next topic, and they'll go fairly fast. They're not long calculations. These are more like mind benders than anything else. We're asked to simplify. What? What in the world? I've got a log in an exponent. I thought logs were exponents. Yes, yes. The fact that I'm sort of double stating things, right? I've got an exponent in my exponents. Hang on and let me tell you how we read this, and it'll all make sense. The way we read this is 42 raised to the power is the word I'm going to use, but we could also say log The way we read this is that it's 42 raised to the power that 42 must be raised in order to get 5. 42 raised to the power that 42 must be raised to in order to get 5. And the answer is 5. What? Basically, this and this cancel each other out in a weird way. You can think of it that way. And this number becomes our answer. 42 raised to whatever power 42 has to be raised to get 5. Well, then the answer's 5, because that's we raised it to whatever power it needs to be. All right? In order for this weird this weird thing to work, this thing that we just did right here, the bases must match, right? This 42 and this 42, those have to match in order for this trick to work. And you'll see in the problems coming up that we can use laws of logs and other things to rearrange here. Okay, because what John's going to do is he's going to play some tricks on us where these bases don't match, but we can rearrange and make them match. The main thing I want you to know is that we can use the law of logarithms on these numbers just as we would any logarithm. Okay, so let's try another one. The fact that I'm starting a problem down here tells you a lot about how much space we're going to need. Okay. Simplify. That's the instruction for all of these. 9 raised to the power that 3 must be raised to get 5. Okay, I said the bases have to match. No bueno. 9 does not match 3. But here's the question. Can we make 9 match 3? Yes, we can. We can rewrite this base as 3 squared times the log of 3, 5. I don't really need those parentheses, but I'm just showing you. I put all of that here, and I changed the 9 into a 3 squared. Okay, now this is a coefficient to this, so I can take this and pop it up on there using the third law of logs. So now I'm writing 3, this is the exponent, log 3 of 5 squared, right? See, I took that 2 and I put it up as a square on the 5. So that's 5 squared, and I can change this now to a 25. And now I've got 3 raised to the power that 3 must be raised to get 25. And so my answer is just 25. Are you weirded out by this? It's okay if you are. It's kind of weird. Okay? It's just a special little trick we can do with putting logs in exponents. All right? And they create this strange little redundancy, and we can just go straight to that number, right? We don't know what the exponent is, but it's saying, here it is too. Raise 3 to whatever power you have to raise 3 to in order to get the number 25. So we don't know what that exponent is, but it doesn't matter. We just know that if we raise it to that power, then we'll get the number that we want to get. I know. It makes my head spin a little too. You can easily recognize these problems though, because, I'll write the next one. We're already up to 6. They have logs in the exponents. Ready? This one might hurt you a little bit. 10. Give yourself lots of room to write. Ooh, this one looks kind of like that other one when we changed the 9 into a 3 squared, because we've got a coefficient, right? We've got a number in front of our log thing. So we want to take, these match, so that's good news. We have to take this and we have to put that here. So now we have to raise the square root of 3 to the 4th power, okay? What that's going to be is 10 raised to the log of 10, and then we have to multiply this. If that feels crazy to you, we have to multiply square root of 3 times itself 4 times. That's 3, so the whole thing equals 9. Now it's nice and clean. Raise 10 to the power that 10 must be raised to in order to get 9. Our final answer is 9. Okay, 7. This one is such a long exponent. Okay, so we know it's one of these crazy run in circle problems because we have logs in the exponents. It's got a super complicated log expression in the exponents, but when we see this plus sign, we recognize, oh, law of logarithms, all we have to do is multiply these two, right? I'll just show you. It's right here. If we're adding Matching bases, we multiply the arguments together. So this will become 3 log 3, 20. So we're taking 3 and we're raising it to the power that 3 must be raised to in order to get 20. So our answer is 20. We don't know what that exponent is, but we know that the answer is 20. So yeah, 20. $59.8. Now this one, I think the way it's written is confusing. This one does not look like our other ones. It does not have a base with a log expression on it. This is just a log expression. So this one is saying that the base is e and that the number is e to the 14th. So it's saying, what is the exponent we put on e to get e to the 14th? And the answer is 14. What is the exponent we put on the base of e to get e to the 14th? 14. It's so easy, it's hard, right? It just is like, what? We're talking in circles. Okay, one more. And then we're done with this weird lesson. $59.9. Okay, this one is similar to the previous one. It's not a log on an exponent. We just have to think carefully about what we're doing here because this log is not a log that we're used to, but this is, or this base, and this is the number. So this is one that we want to change into an exponential again, right? 5 raised to what power? I guess I could put x, not draw a box like we're in kindergarten, equals 25. 5 raised to what equals 25? Oh, 2. Okay. If you even have your fingernails dug in and are hanging on to the edge of understanding what in the heck I'm talking about, you're doing fine. These latest problems are a third subset of what we're doing down here, right? They're rearranging, simplifying. They focus on the laws for logarithms. They're neither this nor this, but they're a weird third category. All right? So what I'm going to do is I'm just going to add a third category here, and I'm going to write weird. If you want to add that to your sitemap of the different log problems we've been doing. I'm calling these the weirdo problems. And I think actually, honestly, once you sleep on it and do a few lessons of homework, you'll see they're quite harmless, but they're really strange. They're like no, I'm not gonna, I was gonna make a metaphor about cats that you don't know, and are they gonna bite you or scratch you or just purr, and they all purr. So there, I did it anyway. I couldn't resist a metaphor. Okay, that's lesson 59. Thank you, goodbye.